Okay, so here's where we were last time. We were looking at the strategic diagram for R3. Do make sure to notice that there's a totally different diagram here for R3 compared to R2, where there's a lot of similar ideas, but the geometry of R2 is just importantly different from R3 in certain ways. So we really have to have a whole new diagram. So we talked through some of the big ideas on this diagram last time. I'm a big fan, by the way, of this diagram. Again, that I've hinted vaguely throughout this semester, mostly in the last couple of weeks, that a lot of the ideas in chapter 6 and 7, it's all the same idea. They all fit together. They're all unified by a more sophisticated construction that we just can't talk about. Right? So what this diagram is that the boiled down, under structure, bare minimum. Here's what you need to know. Here's how the rubber meets the road, of the sophisticated point of view that we can't talk about in detail. But again, boiled down to, how does it manifest itself in what we do in this course. So there's tremendous, value and, power in this diagram. Okay, so one of the things we talked about is how, the fundamental theorem of line integrals, for example, you can kind of think of as being this little pattern, that if you have a function and you compute its gradient, if you have a curve and you look at its endpoints, and if you evaluate kind of on each side, appropriate to the way you do that kind of thing in that context, then you get the same thing both ways. So, fine. And so what? Well, the so what is that this pattern holds, right? So this geometric visual, let's say, pattern on the diagram representing the fundamental theorem of line integrals, it's the exact same pattern for Gauss's divergence theorem. It's the exact same pattern. Stokes' curl theorem, boom, exactly the same pattern, right? So when you think about these theorems in the context of this diagram, notice you don't even have to think of them as 3 separate theorems, arguably 5 separate theorems, arguably 6 if you count the fundamental theorem of calculus in the R1 sort of version of this, right? They're not separate theorems to be memorized independently of each other. It's one pattern to be digested in the context of the diagram. So if you make sure to understand the diagram and memorize the diagram, then you just cut your workload by a factor, right? So really powerful idea. By the way, let's talk about memorizing this diagram. It's not as hard as it looks. In fact, we can even look over here to the this is the sort of expanded version that I have as a page in my textbook in another context. By the way, this page is available on Sakai. It's there's a file in the resources section called diagram.pdf. It's exactly this page. It's sort of just a stretched out, expanded out version of what we have in the notes. I lost my train of thought. Memorizing the diagram. It looks like a lot to memorize. It's really not. You have to know the order that these operators go in. That you do have to remember. Grad, then curl, then div. That you have to memorize. Other than that, everything is patterns. And sort of, things that you couldn't unmemorize if you tried, right? What kind of evaluations do we do possibly, conceivably, when you have a scalar valued function and a 3-dimensional region? Triple integral is the only such kind of integral we've ever talked about. So, do you have to memorize that, or is that sort of obvious? What else could it be, right? And sort of likewise down the road. So you need to know the order of these operators. I claim that's pretty much it. Then you do also need to remember what the pattern is for the theorems, right? Other than that, everything else kind of naturally falls into place. You don't so much really need to memorize that when you have a surface and you look at the boundary of that surface, that's a curve. Well, of course it is. That's just good geometric sense, right? Okay. So I encourage everybody to memorize this diagram And I claim you may have accidentally already memorized this diagram inadvertently, right? But if you haven't, then please do. It'll totally pay off. In fact, as a test of that, at your leisure sometime soon, pull out a clean sheet of paper, see if you can reproduce it. You might surprise yourself. Okay, so anyway, back to the diagram. Well, let me go ahead. I'll just work on the bigger, stretched out diagram. So we talked about this pattern. Well, I'll do it over here. And we talked about this pattern that holds for Stokes' theorem and the fundamental theorem of line integrals and Gauss's divergence theorem, etc. Here's another pattern that we kind of talked about previously, but I didn't really flesh it out fully on the diagram yet, and that is that there are special vector fields. I think I may have done this for 2 dimensions. I want to do it again in 3 dimensions for reasons that you'll see in a moment. There are some special vector fields in this, what you might call column 1. They are the vector fields that are the gradient of something, otherwise known as gradient fields. These are special vector fields. By the way, they are also vector fields whose curl is 0, otherwise known as irrotational vector fields. Because, of course, curl is a measure of how much of a rotational aspect there is to the fluid, and if that's 0, then there's no rotation, thus irrotational. Same vector fields. 2 different properties, same vector fields. They are also the vector fields that are path independent, and you may recall the way I like to represent that is that when you have 2 curves with the same boundary points, then they will give you the same value of the line integral. Right? That's a special vector field. And again, path independent vector fields, same vector fields as gradients, same vector fields as irrotational. Now, when you have a path-independent vector field, there is an alternative tool that you could use, conceivably, and if you can make it kind of work logistically. But anytime you have a path-independent vector field, it is a gradient, which means that it has an anti-gradient, which means that you could use the fundamental theorem of line integrals instead. That's on the table. It's an option. And then there's the question of exactness, what I'm going to call exactness, which of course is just the fact that these 2 operators have this feature of exactness. Namely, if it comes from the left, then on the right you get 0, and if on the right you get 0, then it comes from the left. Right? That exactness, how did we demonstrate that exactness? We made an argument that hinged on Stokes' curl theorem. All right, now what we have here on the diagram summarizes many pages of discussion in the notes. Right now, it's lots of details. That I'm not saying this is an alternative for those pages, but this is a compact representation of many pages of discussion, probably several hours of y'all listening to me talk. Right? This is all sort of compactly represented right there. And here's the beautiful fact: we also spent hours of discussion time, pages and pages of notes, talking about a different category of vector fields. It's the vector fields that are, I'm going to highlight here now, I'll use red, vector fields that are curls, for which divergence is 0, as we argued using Gauss's divergence theorem. Which are, of course, also those vector fields that are surface independent. And because they are curls, another option on the table for how to compute, if you can make the logistics work out, is Stokes' curl theorem. So, again, it's just shocking how much the patterns hold, right? So everything that we said about these special vector fields that you might, just for convenience, I'm going to call them gradients, are special for all of these reasons. Well, likewise, curls are special for all of these reasons. Right? So now there's a tremendous amount of value in noticing the power of this pattern that everything holds together one dimension up, right? So in particular, where the payoff is let's suppose you can't remember how, wait a second, was I supposed to make the case that we have this exactness here? Why is it that the divergence of a curl is 0? Where did that come from? Well, what you can do is ask yourself the analogous question about gradient fields. In the context of gradient fields, you may remember there's sort of easier pictures to draw, perhaps. You've had more time to sort of digest it. And, with gradient fields, it was the curl theorem was the thing that filled in this exactness that allowed us to conclude that exactness up there. Well, then by analogy, you can speculate with pretty great confidence, and you'd be right that because of the analogy, that means that it must be the divergence theorem that makes that connection for curl fields. So I'm just a huge fan. I'm a big proponent of thinking about, organize all of the ideas that we've learned in this course in terms of this layout on this diagram. So, okay. All right. And then lastly, I'm going to claim, and we're going to see this develop as we go through the rest of the pages here, that they're very powerful. The diagram's a very powerful tool for helping you compute line integrals and surface integrals. Now, a lot of stuff's going to kind of come together today. A lot of, we're going to see how all the tools that we've been accumulating over, no pun intended, over this last several weeks they all fit on the diagram, and you can make use of that diagram to diagnose what kind of a problem it is that you're looking at. Okay, so the broad strokes are always going to be, look at the diagram, see where you are. That's going to give you context. Very, very useful. So, for example, looking at this first example we have right here, it says compute a line integral. Okay, so apparently I'm in the line integral portion of the diagram. Now, which diagram, important point, notice that my curve here has 3 coordinates. That means I'm in 3 dimensions. Likewise, alternatively, you can look at your vector field, 3 components, right? So again, we're in 3 dimensions. So the context from the diagram for this question is in R3, looking at line integrals. And that puts us, here's R3, here's line integrals. That puts us looking at these 2 theorems as possibly relevant theorems, right? Said differently, this is my context. Everything I should be interested in concerning this question will happen within this zone here, right? And this saves you having to wonder about some things. I wonder if Green's operator is going to be relevant to this question. Nope. Not even on this. It's on a totally different diagram. Doesn't have anything to do with anything. Right? Maybe divergence? Should I compute the divergence of this vector field? No. Oh, no. Don't even write that on your page. Right? If you write down divergence on your page, the grader, by the way, FYI, I probably will not be grading, certainly possibly any of the questions on the final exam, right? So on the final exam, don't assume that, me and my standards are going to be, where the points are going to come from. The grader might look at a situation like this where the question was about a line integral, and if you have divergence written on the page somewhere, that's kind of a dead giveaway that you're kind of grasping at straws, right? It's not a good look, right? So it's going to make the grader suspicious of everything else you've written down on that question. And you don't want to have a grader who kind of goes into your work thinking, I don't think this person knows what they're doing. Right? So don't even write down divergence on the page. Likewise, no triple integrals. I don't want to see the word Gauss. Right? Anything that's outside of the context that the diagram gives you is a bad look. Does everybody see what I'm talking about? Okay, so that's going to save you what I'm going to call benefit of the doubt from the grader, to not put anything on there that that doesn't look good. Okay, so there's the context. Let's see. Back to the question. It says here in our summary, next thing, compute the appropriate operator and the appropriate boundary and infer from that. Okay, so back to the diagram. The diagram tells me if I'm interested in a vector line integral in R3, whatever vector field I've been given, this says compute the curl. And from that, we may or may not be able to draw some useful consequences. But just go ahead and compute it, because the diagram's telling you to. Whatever curve I'm given, look at its boundary points. We might be able to infer something from that, but these are the natural things to do, right? So go ahead and do it, and here we go. Let's compute the curl of this vector field. All right, so by the way, my little hack, this is a personal, you don't have to do this, but remember when you're computing curl, there's actually a kind of a 3x3 sort of symbolic matrix, and I, J, K, and then partial with respect to X, partial with respect to Y, partial with respect to Z, right? And for me, I don't know, I find it convenient in my mind to just visualize that as I'm doing the computations, but I find that really most of what I need is just, it's helpful to have kind of that written down, or at least in my mind. So to compute the curl, step 1, I need to take the y partial of that and then subtract the z partial of that, which gives me 1 minus 1, which is 0. Cool. Next, I need to take the z partial of that minus the x partial of that. Okay, that gives me 2x minus 2x. Also 0. Cool. Third coordinate will be the x partial of that minus the y partial of that, which is 2y minus 2y. Okay, so cool. We computed curl, and the curl is 0. And that gives me good news. Curl of f is 0. That means that there is an antigradient. Right? Again, diagram tells me so. I computed, I had a vector field, I computed the curl, I got 0. That tells me that there is an antigradient, a function whose gradient is that vector field. That means fundamental theorem of line integrals is on the table. Right? Is everybody on board? Notice you don't even really particularly have to remember the details there. You're just following what the diagram says. Well, I'm here. It says to compute this, and then remembering the pattern of exactness is what tells you this, and then remembering where the fundamental theorem of line integrals falls tells you that this is your option. Yep.
If you didn't get 0, would you just continue from start?
Yeah. Well, then yeah, that's right. Then there's another question to ask. But if you have a vector field, you compute the curl, you get not 0. That tells you there is no antigradient. That says don't even think about the fundamental theorem of line integrals. But yeah, yet to be addressed is the question of whether Stokes. Yeah, exactly. Everybody good? Okay. Yeah, all right. So anyway, we got 0. Antigradient is there. Fundamental theorem's on the table. Now, the next thing the diagram tells me to do. For my curve, I need to look at the boundary points. Let's do what the diagram tells us to do. Here we go. Let's see. I'm going to plug in t equals 0 into there. See what we get. And I get x of 0 is, well, let's see, 0, 1, 1. Right? And now, next, I'm going to plug in 1 into there. See what we get. And we get x of 1 is -1, comma. By the way, don't trust my arithmetic, please. I'm prone to arithmetic mistakes here. Let's see. 1, comma, e squared. Okay, what conclusion do we get from this? This curve starts and ends at different points. The curve starts like there or something, and it goes on and does all sorts of weird things, and it ends at a different point. What do I conclude from the fact that these start and end points are different? It's not a closed curve. This is not the boundary of anything. There is no surface that I could possibly use with Stokes' curl theorem. So what that tells me, because I computed the curl, I computed the boundary, I did not get 0, did not get nothing. I got an actual couple of boundary points, and that means there is no anti-boundary surface. That means there is no Stokes' theorem on the table for this question. Everybody on board? Now, I dragged this argument out, to show how we're using the diagram and all the patterns, etc., to draw these conclusions, but you can do this really quickly, right, at a glance sometimes, depending on the algebra involved. And if you have this diagram memorized, as you close your eyes and you can still see it, right, then just at a glance, let's see here. Let me compute the curl. Okay, 0. Cool. I have the option. The two endpoints are different. This is not, forget Stokes, right? You can do this in 10 seconds. And what this tells you is that you have a single accumulation theorem that you can use on the table, and it's a good one. It's fundamental theorem of line integrals. That's how we're going to solve this problem. This is a fundamental theorem of line integrals question. How we doing? Everybody on board? So, cool. I just need to find the anti-gradient. I'm going to leave the algebra of that to y'all. Of course, y'all are fully capable of taking various anti-partials, and playing that little game and putting the pieces together. You find the anti-gradient f. We know that this line integral is going to be f of b minus f of a. We have those points computed, right? My starting point is there. My ending point is there. That's all details from here. How we doing? So, by the way, notice there's a tendency to look at the sort of the blue part of what we have here. I computed the boundary points, and all that did is tell me what I can't do. All this did is eliminate an option. Arguably, that's was a waste of time, but no, it wasn't, because knowing those boundary points doesn't just eliminate an option, it's also telling you what those points are that you'll be using in the theorem that we already agreed you can use. Right? So very often these computations suggested by the diagram are multi-purpose. Okay. All right. Moving along, unless anyone has questions. Yeah.
If the 2 points were the same, you'd be using Stokes.
Well, then it'd be a possibility that I might be able to use Stokes. I mean, I'd still, I'd have to compute the curl. Again, we've already done that. That's nice, right? And then I'd have to think about, okay, well, what surface is it? I'm going to still have to think through what is that surface that is called the anti-boundary, right? So there's other details, and it might not be worth. It may be that fundamental theorem of line integrals is still the easiest option. So it's not like you have to. When you have, in those scenarios, when you have both options on the table, you don't have to do either one in particular. You can just do whichever one looks easier to you. Yeah. Is that cool? All right, let's do the next one. Okay, let's see here. Let's move faster this time, just because I want you all to see how fast one can move. We're in 3 dimensions looking at line integrals. That, again, 3 dimensions, again, looking at a line integral. Again, these are my options. Again, we are not going to have anywhere on the page a divergence or triple integral or the name Gauss, and not on the page, right, of your work because it's a bad look, right? So we know that. Now we also know that we need to, apparently, where's my colors? I need to compute the curl, and I need to take my curve and look at the boundary points. Doing what the diagram tells me to do. It's done all the sort of organizing for me. So, okay, we compute the curl. By the way, the curl is the 0 vector. Can anybody do that algebra that fast? Let me show you the trick for how you can see the curl is 0. We know we're going to be taking the following partials, right, in that sort of determinant, symbolic determinant sense. And notice there's only x's in the first coordinate, but I'm going to be doing only y and z partials. Obviously 0. Likewise, there's only y's in the y component, of which I'll be doing only x and z partials. And there's only z's in the z component, of which I'll be doing only x and y partials. The partials you're going to be computing are just at a glance 0. So anyway, that's a 30-second time saver. It's not an important point, but nevertheless, I like little time savers, so something to be on the lookout for. Okay, so curl is 0. Cool. Fundamental theorem on the table. Now notice, I didn't have to have the diagram in front of me to do that. I have memorized. I have this printed backwards across the back of my eyelids. And so I just already know that because the curl is 0, that means there's an anti-gradient. That means fundamental theorem option. Okay, now, looking at the next thing. We're going to take our curve and look at the boundary points. All right, fine. You plug in 0. You plug in 1. Now, there's some arithmetic to be done here. And we've got x of 0 is 0, 1, 1. Please catch me if I make a mistake. Now we're going to plug in x of 1. Okay, then I get 0, 1, 1. This curve starts and ends at the same point. Now, again, you can let the diagram do the work for you, and the fact that there is no boundary, you might say, means that there is an anti-boundary surface, and that means that Stokes' theorem is on the table. So we've got our options. We can go either way on this one. You can use fundamental theorem, or you can use Stokes. Everybody happy? Let's do Stokes for this one, just cause, right? We did the fundamental theorem on the last one. So, yikes, this is a horrifying curve, right? It starts somewhere and it goes around and it does all sorts of, some sort of weird stuff to come back to the same point. I don't know that I can figure out what this surface is. And so there's a temptation to say this is a bad approach. We don't want to try. I have no idea what surface is going to be in there. That curve's probably not in any single plane that I could. This is going to be a weird thing, right? But here's the thing. Let's write down what Stokes' theorem says. Stokes' theorem says that the line integral is a flux through this mystery surface of curl dot ds. But wait a second, we already computed the curl. The curl was 0. Right? So as previously observed, because the curl, I should write this down anyway, we've already computed that curl was 0. That means we're taking a flux of 0. The answer is 0. We're done. We walk away. Is that cool? So again, it was a multi-purpose use of that part of the diagram. So we computed curl partly in the interest of deciding whether or not fundamental theorem's on the table, but it paid off as well by that curl I computed being my integrand in the use of Stokes' theorem. Everybody with me? Okay. Cool. Moving along. Another line integral. Again, 3 dimensions. Let's see. I need to be in highlighter mode. R3, computing a line integral. There's just more interesting things to talk about in that part of the diagram, so that's where I'm focusing. Okay, so same things. I need to compute the curl. I need to look at I don't have a parameterization, so I'm going to have to visualize this curve and sort of visualize the boundary and whether it, is this a closed curve or is it not a closed curve? Let's see here. Let's compute the curl first. And let's see here. Again, don't trust my arithmetic. I get -1, -1. -1. Does that look right? Correct me if I oops. There's the curl. It's not 0. Again, clean things up. We are looking at this. I computed the curl, not 0. There is no anti-gradient. Forget about the fundamental theorem. Again, don't even write this on the page. If you write f of b minus f of a on the page, it's a bad look, right? So just leave that off. Or if you've accidentally already written it down and then subsequently you compute this and realize, oops, I would advise scratching it off. Right? Just so that you communicate to the grader, I realize now that there's nothing down that road. Okay. So, next thing, let's visualize the curve. I need to understand if my curve is a closed curve or not, and let's see, let's draw the picture. All right. Well, we have a cylinder. And we have a plane. Okay, so this will be hard to draw. Something like that. My curve is the intersection of these two things. How does this plane cut through that cylinder? All right, well, look, my art is going to be there's an upper bound on how good that's going to be, but you can kind of see how that plane cuts through that cylinder, and it's going to make a curve that looks kind of like that. Plausible? All right. Now, is this a closed curve? Yep. I mean, just picture, right? The picture answers that question for me. It is closed, and it also simultaneously, you can even see what the anti-boundary surface is. It's that flat plane, that flat two-dimensional solid ellipse, you might say. Right? There's our anti-boundary surface. So Stokes' theorem is an option. All right. So if I were to use Stokes' theorem on this, this would be I would have to compute the flux through that surface of f. Dot ds. Curl f. Curl f. Dot ds. I'm going to write dot little n ds scalar because I'm looking at this picture here and realizing, hey, you know what? I'm kind of hoping to avoid parametrizing this surface. Not that I couldn't, but all else being equal, let's fingers crossed, maybe we'll get geometrically lucky. I do notice that surface is part of this plane. This plane has an easy normal vector. I can basically read off of this equation. You got to worry about orientations and stuff like that, right? But it's look, 1, 1, 1, and so I'm going to just go ahead and put in 1, 1, 1 here, and divided by square root of 3. Got to make it a unit vector. I'm going to put in a plus minus question mark in recognition. We haven't thought about orientations yet, but there is the possibility that this dot product might just be sort of obviously convenient. Now let's take a look though. Curl and dotting with 1, 1, 1. I get a constant. That's kind of cool. But it's not 0. So I'm still going to have to compute, even if even given that constant is easy, I do still have to compute the surface area. The surface area of this thing is not immediately obvious. It's not a circle. It's an ellipse, but it's not particularly clear what that major axis is. I think we made a noble effort here to get lucky, but it just didn't come out. It didn't work out. So if only to compute that area, we're going to have to parameterize this surface. Not that it's the worst thing in the world, but this is starting to look like it's still work. So frankly, I'm a little disappointed in Stokes' theorem's utility in this case. Does that make sense to everybody? And we can do that. We can parameterize it. It's easy to parameterize. By the way, let's talk about how to parameterize. The surface in question is, again, it's part of this plane that has that equation, and that equation is a graph. You can just solve for z in that equation. Is that cool? I've got a better way to solve this problem. And again, I think we made a noble effort here, but here's what I think is the easier way to solve the problem. I'm going to slide all of this down out of the way. Well, you know what? I'm still going to slide that all out of the way, but I do kind of need this picture, and I'm going to, for time reasons, I'm going to allow myself to just steal what I need here. Okay, so there's my curve. And here's the thing. Here's the easier way to solve this. I think easier way to solve this problem. That curve is itself actually pretty easy to parameterize. Now here's how I know. That curve, it's a weird curve, but look, the x and the y on this curve, no big, right? The x and the y are just going around in a unit circle. That's easy. Right? And so the projection down here into the XY plane, you might say, is just almost a freebie. And let's see, we can just immediately write down, in other words, that, let's see here, X and Y are, I'm going to do cosine t, sine t. Because of the cylinder aspect of the problem. What's z, though? How do I figure out what z is? Well, notice that's kind of given in the other equation. It says right here that z is negative x minus y, because that blue surface is also part of what defines my orange curve. So negative x minus y, and I already know x and y. So I have here minus cosine t minus sine t. So, honestly, I think in this question, I think the easiest way to solve it is just go ahead and parameterize the curve as is. Vector field's not scary. The parameterization's not scary. I think the easiest way to solve the problem is what we're looking at right here. I would just parameterize, I would brute force this question. How we doing? Does everybody buy it? Now, if you want to do, if someone were to do Stokes' theorem instead on this question, that also works out reasonably well. No problem. Use whichever one you like better. Perfectly fine. But what I like about this example is it points out that these accumulation theorems we've written down, they're tools. They're not magic wands. It's not like they're always going to make a question easier. Sometimes they do, sometimes they don't. Sometimes they apply, sometimes they don't. And again, when they do apply, they may or may not be beneficial. Very often they are. All right, is everybody happy? All right. Okay, looking at number 4, you'll notice a lot of similarities here. We got the same vector field. We got a cylinder and a plane. Very little different here, but there is a critical difference. So this is another scenario that can come up. Let me draw the picture again quickly because it's a very similar picture. Come on. There we go. The cylinder a plane. Now this is, again, a different plane. Let's see here. I'll use blue again. X equals Z. Now, it's kind of a hard one to draw well, but and the intersection is going to be, I don't know, something kind of like that. It's hard to make this one look, good, but you don't have to overthink certain aspects of your diagram. Very often, qualitatively accurate is sort of good enough. And don't worry about whether the perspective is perfect. Okay. So here's the key difference. It remains, the curl is still -1, -1, -1. This time, though, my normal vector, still easily readable from my equation of my plane here. My normal vector is, let's see here, 1, 0, -1. Okay, there's a plus or minus question that I haven't addressed yet. And yeah, I got to divide by the square root of 2 to make it a unit vector. But I can see right away that if I were to take Stokes' theorem here and rewrite this as flux of curl dot little n ds, I can see that dot product happening in things that I've already easily observed. Dot product's obviously 0. Boom, we're done, we walk away. So sometimes Stokes' theorem is a massive payoff. You could parameterize, but you'd be doing a lot of I'm going to say unnecessary tedium. And furthermore, keep in mind, the way that this gets graded, what we're looking for when we're grading your work, it's not about the answer at the bottom of the page. Get there however you feel like it. No. We're looking for demonstration of proficiency with all of the ideas. And if you miss out on the really beneficial, easy way to solve the problem, it's, again, not a good look, right? It makes it look like you didn't even notice the much better solution. So don't be surprised if you didn't get full credit if you did this the parameterization way. Just saying. That makes sense? Right? Again, we're looking for proficiency with the ideas. The big idea here isn't the answer at the bottom of the page. The big idea here is how awesome Stokes' theorem applies to this circumstance. Make sure that you demonstrate understanding of that big idea for this question. Let me pause on this for questions. How are we doing? Okay. Number 5, on to fluxes. Now again, we're still in the R3 diagram. We've spent a bunch of time doing two-dimensional stuff anyway, right? So in R3, this time though, looking at a flux, let's go back to the diagram. Let's make sure we see where we are, what we're doing. We're in R3. We're looking now at a flux. The diagram now gives us different hints or suggestions. On the one hand, the given vector field, apparently I ought to compute its divergence. So says the diagram. Apparently my domain that I've been asked to compute a flux over, I should look at the boundary curve. And let's just see what happens when we do that. Okay, so let's compute the divergence of this, let's compute the divergence of this vector field. Anybody notice any convenient way to compute this divergence? There's a really, look, their algebra is not that bad. It's easy to observe the straightforward calculation, right? But there is a freebie on the page. And that is in the hint. It says right here, F is a curl. All right? Now again, if you've got the diagram printed backwards across your eyelids, right? Then, we're computing the divergence of a curl of something. Oh, that's 0. Don't even have to compute that curl. Now, in this case, that would have saved you about 10 seconds tops of easy partial derivatives, right? But had F been a weirder, uglier vector field, The observation that it's a curl and therefore divergence is automatically 0 would actually be very helpful. Okay. Okay. Cool. So let's see here. 0. Sweet. Let's see here. For the surface we're given, we need to think about what its boundary curve is, at least in relation to, can I view this as being the boundary of a solid? And okay, let's take a look here. My surface is, all right, I gotta draw the picture. That's an upside down elliptical paraboloid. Let me get into pencil mode here. But this says I'm interested only in the portion of that elliptical paraboloid that is above the XY plane. And so I'm actually interested in then just this right there. Is that cool? Now, very, very, very important fact. Notice this surface is not closed. This can confuse a lot of students. I think I made this observation earlier in a different context. The way we would draw, let me just take this right here, that thing by itself. This thing here, this could represent an upside down cereal bowl, or it could represent an upside down cereal bowl with you've already got the cling wrap, so it has an underside surface. You draw it the same way. Unfortunately, the way we draw things is just poor and can be confusing. And frankly, the way this is drawn, it could be that what we've drawn is a solid here. So don't accidentally confuse yourself with these shortcomings of your drawings. You gotta make sure that you think through exactly what was described in the question and which of these many things that this drawing could represent is it actually, right? And notice points that are on the undersurface, you might say. They are not part of this surface. So this is not a closed surface. Is everybody clear on that? Okay. All right. So it's not a closed surface, so I can't use, it's not a closed surface. There is no anti-boundary region. Gauss is off the table. Right? And so, Stokes's curl theorem, I guess, is an option, right? We did compute the divergence. We got 0. We have the anti-curl. By the way, that's a rare aspect of this question here. Not only do we know that this is a curl of something, but this vector field F, we are explicitly given what the anti-curl is. The anti-curl is this thing right there. This is the thing whose curl is F. Right there given, right? So don't pass up on that nice little opportunity. So we know the anti-curl, thankfully, because we don't know how to compute anti-curls, right? So very valuable that this question has actually given us, we know the anti-curl, and we know what that boundary curve looks like, and so the flux that we've been asked to compute, I could alternatively compute that line integral. Everybody good? This question is actually a twofer, FYI. There is a second way to solve this problem. Now, we've agreed that there is no anti-boundary region, so the Gauss's theorem is off the table. But because of the fact that our vector field had divergence equal to 0, there is also the option of surface independence. Right, and depending on the particulars, maybe that would be a convenient way to solve the problem as well. So what that allows me to do here is I can look at this and say, you know what? But the boundary, let me just delete all this. The boundary of my surface is this curve, and I don't like this surface that I was given. So what other surface might I like better? All I got to do is pick any surface I want that has this same boundary curve. I like this nice flat surface right there. right? Wishful thinking, that's valid. It is a surface-independent vector field. That flux is the same through the yellow surface as it is through the blue surface. So all you have to write is divergence is 0. That implies surface independent. And then just start talking about flux through this disk down here. Right? Really easy to make the observation that surface independence is valid. And then you can proceed with that calculation. I think it'd be a nice exercise to go ahead and fill in both of these. Do it both ways. What you're going to find is that they're both actually pretty awesome. Stokes' theorem approach to this flux is actually quite nice. And the surface independence approach, also really nice. So give those a try. Take a gander at your convenience at example 6. This is actually a pretty easy one, but I'll bet you can do this on your own. And y'all have a good rest of the day. And let's see, this is Friday. Yeah, so see y'all on Monday for Chapter 4. Where's the